Hello and welcome to today's class. Let's look at the study of radioactivity in chemistry. Radioactivity, let's look at radioactivity in chemistry, and also we'll look at types of radiation. We'll also look at the concept of alpha particle, beta particle, and gamma ray or gamma radiation. Proceeding, we'll also look at the concept of natural activity, natural radioactivity, and the artificial radioactivity, and also look at the concept of alpha decay and beta decay. And also, having explained all that, we will now solve past questions for JAMB and WAEC, and also higher institution past questions based on radioactivity. By definition, radioactivity is the spontaneous decay or disintegration of the nucleus of an atom of an element where it emits alpha particle, beta particle, gamma ray, or a combination of any two or all three, and energy. The energy given out through a radioactive is called nuclear energy. So the energy given out through a radioactivity is called a nuclear energy, and it comes in. So this becomes the basic idea behind radioactivity. So the energy or perhaps the energy produced by a radioactivity is called nuclear energy, which is in form of heat. So when it comes to radioactivity, there it's simply a spontaneous decay or disintegration, right, that emits alpha particle, beta particle, or gamma ray, right? So or the combination of all three. So that becomes like the basic idea behind radioactivity. And that's, by the way, it's important to note that radioactivity was discovered by a French physicist called Henri Becquerel. So Henri Becquerel was a French physicist who discovered radioactivity, and it was from this generation in the year 1896. So it was from this concept that nuclear bomb was invented, and this concept here counters John Dalton's theorem. So this concept here distorted John Dalton's theorem that says that atom can neither be created or not destroyed, right? So this concept here distorted that concept. Why? Because from radioactivity, they were called nuclear fission and nuclear fusion. So nuclear fission there has to do with combining atom, and nuclear fusion has to do with the distorting atom. That's the concept there. So here's the concept. A French physicist called Henri Becquerel discovered radioactivity in the year 1896. All right, having explained the introduction to radioactivity, let's proceed let's look at the next concept called type of radiation. Let's look at the concept of types of radiation. Let's look at types of radiation. Let's look at types of radiation. From the definition I gave you for radioactivity, we said it is spontaneous decay or disintegration which emits alpha particle, beta particle, or gamma ray or gamma radiation. So those alpha particle, beta particle, and gamma ray are referred to as type of what? Radiation. So number one there, I have alpha particle, alpha particle. Number two there, I have beta particle, and I have number four, I have gamma ray. So gamma ray radiation, or you call it gamma ray. All right, so I have alpha particle, beta particle, and gamma radiation, or you call it gamma ray. Please, gamma Gamma is not called gamma particle. Of course, I have alpha particle, beta particle. This one here is not gamma particle. It's called gamma ray radiation, or call it gamma rays. So this becomes the basic types of radiation we have. Let's discuss this radiation one after the other. Let's look at alpha particle, let's look at beta particle, and let's look at gamma radiation. So we'll be looking at the characteristics of each of them and pick out some points from them, and then we'll proceed. Let's start the first one called the alpha particle. Alpha particle are positively charged helium nucleus moving at a speed of light and are relatively massive. They are slightly deflected in the magnetic field and have very little penetrating power. Example, a finite sheet of paper. So that's like the explanation to alpha particle. So alpha particle are slightly deflected. They move like a speed of light. Also, they are called particle because they are relatively massive, right? And let's do number 2 and 3. So let's do number 2. Let's do number 2 and 3, and then we'll try to explain them as we proceed. Let's explain beta particle. Beta particle are high energy electrons and travels approximately at the speed of light. They are relatively light and are strongly deflected in the magnetic field. They have good penetrating power and a penetrating several millimeters of aluminium. So that's like the explanation to beta particle. Let's look at gamma ray radiation or gamma ray. Gamma ray are electromagnetic wave of several wavelengths which travels at a speed of light and are electrically neutral. Their masses are negligible. They give small or no effect to a magnetic field and have highly penetrating power in air and solid. Example, many centimeters of lead block. Alright, that's basically the concept behind alpha particle, beta particle, and gamma radiation or gamma ray. Let's explain this, please. Now, here's the concept, please. First things first, from like what I gave you earlier now, I gave you the characteristics of each of them. Check your notes. I'm saying this, please. Alpha particle are helium nucleus. That's the first thing there. Beta particle are electrons, while gamma ray are electromagnetic waves. That's first task. Next and again, alpha particle and beta particle, these two are called particle. Why? Because they are relatively massive, like they have little masses in them. So when something is relatively massive, it means they have masses in them. So alpha and beta are called particle because they have a smaller particle in them. Gamma ray, the mass are negligible, right? So it means that gamma ray has like doesn't have mass. If even has the mass, like tiny mass, so the mass is negligible. So that's why it's called gamma radiation or gamma ray. Also, another thing to note is that for alpha particle, they travel at speed of light. Similarly, beta particle travels speed of light, and gamma ray also travels like its speed of light there, right? We'll take a few diagram illustrating these three radiation in terms of electric field and magnetic field, right? So look at two diagrams. One explain magnetic field, the other explain electric field, such that I will play a role of alpha, beta, and gamma into the diagrams. So let's look at how you can relate these three into electric field and magnetic field, what they mean. All right, all right. So I have a diagram that shows how alpha, gamma, and beta particle are playing when it comes to magnetic field and when it comes to electric field. Now, here's what to note, please. This one here, this stuff you're seeing here is called lead block. It's called lead block, right? This one here is called the radioactive element. So it's called the radioactive element. So here's the concept. The radioactive element, the element tends to spread out during the process, but this lead block is used to prevent the radioactive element from spreading out to the environment or to the surroundings. So I'm saying that this lead block is used to prevent the radioactive element to spread out to the environment. And also, gamma ray tends to have more penetrating power, right? It has a high penetrating power. So that when it penetrates to this radioactive element, it tends to spread out. But due to the lead block, it helps to prevent the radioactive elements from spreading out to the surroundings. Also, if you observe closely, this one here, this line you're seeing here, is called the photographic plate. Photographic plate. All right, this one you are seeing is called the photographic plate, right? So here's the concept. Observe that when it comes to alpha particle is moving towards what? South pole, while beta particle is moving towards what? The north pole. And also observe that the alpha particle are slightly deflected to the magnetic field. Observe. So alpha particle are slightly deflected to the north-south pole, if you observe. So alpha are slightly deflected when it comes to magnetic field, while beta particle are largely deflected. You can see they have most largely deflected. So this one's not largely deflected. So I'm saying this, please. When it comes to magnetic field, alpha particle are slightly deflected. When it comes to magnetic field, beta particle are largely reflected. Why the gamma ray has we said the mass are negligible. So like it has no deflection. So you can say it has no deflection. So yeah, this like alpha particle, beta and gamma ray in under the concept of magnetic field. Let's look at electric field. For electric field, yes, this is still your lead block, your radioactive element, your photographic plate, right? Observe that I have alpha, which are alpha particle are positively charged. So each positive charge means it's moving towards what? Negative charge. Also, beta particle are negatively charged. They have to move towards what? Positive charge. In accordance to the first law of electrostatics that says that like charges repel while unlike charges attract. So these two are unlike charges, they will attract. These two are unlike charges, they will attract. So that's like the concept of alpha particle, beta particle, and gamma ray in terms of electric field. Also note that the deflection are almost like the same thing. So when it comes to electric field, the deflection of alpha and beta are like the same thing. When it comes to magnetic field, the deflection of alpha is slightly, right, and the beta is what? Largely reflected. So observe the difference between the two diagram I have for magnetic field and I have for electric field. All right, let's proceed to other concepts. Let's look at next concept called types of radioactivity. For this one here, there are two types of radioactivity. We have number one, the natural radioactivity. radioactivity, and number 2 there we have the artificial radioactivity. So there are 2 types of radioactivity. Number 1, natural radioactivity, and number 2, we have the artificial radioactivity. Let's explain them one after the other and then we'll proceed. Let's at the first one, number 1 there. Let's look at the first one called the natural radioactivity. Let's look at the first one called the natural radioactivity. By definition, natural radioactivity is spontaneous decay or disintegration of the nucleus of an atom of an element where it emits alpha particle, beta particle, gamma ray, a combination of 2 or all 3, and energy. That's how you define natural radioactivity. Alright, when it comes to radioactivity in general, you hear the word spontaneous decay or disintegration. The decay there, when I define natural radioactivity, you hear the word decay or disintegration, right, of alpha particle, beta particle, and gamma ray, and etc. Now, here's the concept behind decay. The decay there are of 2 forms. So let's look at decay. So let's use decay to explain natural radioactivity. Let's look at the concept of decay. All right. When it comes to decay, there are 2 types of decay. Right? There are 2 types of decay, which we call the alpha decay and beta decay. Number 1, we have the alpha decay and beta decay. These are the 2 types of decay that we have. Let's explain one after the other. For alpha decay, please. Number 1, for alpha decay, let's look at alpha decay. For alpha decay, the atomic mass is reduced by 4, while the atomic number is being reduced by 2. For an alpha decay, the atomic mass or the mass number is reduced by 4, while the atomic number is reduced by 2. That's I identify alpha decay. Number 2 is called beta decay. For a beta decay, the atomic mass or the mass number remains the same, while the atomic number for a beta decay, the atomic mass remains the same. For a beta decay, the atomic mass remains the same, while the atomic number is reduced by 1. So it's increased by 1. Why the atomic number is increased by 1. So I'm saying that for alpha decay, the atomic mass is reduced by 4, while the atomic number is reduced by 2. Beta decay, the atomic mass remains the same, while the atomic number is such that is increased by 1. Let's explain alpha and beta decay using some equations. Let's say I have an element X this way, and having atomic number Z and mass number A, such that this element undergoes alpha decay. We said for alpha decay, they have helium nucleus. So it means that a helium will be produced. Helium has atomic number 2 and mass number 4. It's constant. So whenever you see an helium, it indicates what? Alpha decay. So if this element undergo alpha decay, the new element form will be such that, let's say I have Y. Let's assume Y is a new element formed. What will be the mass number and the atomic number of this new element? We said the atomic number of alpha decay is reduced by the atomic number is reduced by 2. That becomes Z minus these 2 minus 2. So the atomic number is such that is reduced by 2, while the mass number, this is A, is such that is reduced by what? By 4. So I have this place. It becomes the equation to alpha decay such that the atomic mass is reduced by 4, while the atomic number is such that is reduced by 2. This explains alpha decay. Let's look at beta decay, please. Let's say I have an element X this way, having atomic number Z and mass number A, such that this element undergo a beta decay. For beta decay, check the definition I gave earlier. We said beta decay are electrons, right? So each being electron has something of this nature, electrons, -1 and 0. So the atomic number of electron is -1, while the mass number is 0. So this is a constant. Anywhere I see E, it signifies all the beta. Anywhere I see He, signifies all the helium. Alright, so if this element undergo a beta decay, the new element we form will be such that we said the atomic mass remains the same. So if A is here, I'll have A here too. Atomic mass remains the same. Why the atomic number is increased by 1. I'll have Z. This is Z minus in a bracket -1. So -1. The Z minus is plus 1. So I'll have Z plus 1. So this shows that the atomic number of for beta decay, the atomic number is increased by 1, while the mass number remains the same. This basically explains alpha and beta decay. Let's look at some example under this and see and understand in-depthly how alpha decay and beta decay works. Let's take an example. Example under this, please. Example under this. When uranium-226 decay to form radium-222 as given below by the equation below. Now look up, please. Someone says when uranium-226, by the way, when radium, please, when radium-226, by the way, radium is abbreviated as Ra. So radium-226, so the mass number is 226. By the way, the atomic number of radium is 88. So the expect I should know it. So they said when radium-226 decay to form uranium-222. So when uranium-226 undergo alpha decay, please, alpha decay. So this one undergo alpha decay. For alpha decay, we expect helium, He, 2 and 4 here. Yeah? So this what's it called? This radium undergo alpha decay to form radon. So plus radon is Ra. Rn is radon. So form radon 222. So they give us the mass number as 222. The mass number as 222. Let's try to get the atomic number of radon. So here's the concept, please. We said Ra is called radon. Radium, and Rn is called random. It's called random, right? So I have this place. So here's the concept. Radion is undergoing alpha decay to give a new element known as radon, right? Known as radon, which is having the mass number 222. Well, let's try to get the atomic number. For alpha decay, we said the atomic mass is reduced by 4, while the atomic number is reduced by 2. So to get the element, the atomic number here, I'll simply do 88 minus 2. These two here, that will give 84. So I have 84 here. So 84 here gives me the atomic. So all right, I made a mistake. I added 88. Sorry, I said 88 minus 2. I said 88 minus 2 should give about 86, not 84. Please, I have 86, so I have 86 here. So to get the atomic, what's it called? Atomic number is easy as subtract this from this. Because we said the atomic number of an element under alpha decay is such that it's being reduced by 2. So subtract this 1 by 2, I have this answer here. So, and of course, please always add plus energy at the end of the equations. The energy produced during reactivity is called the nuclear energy, or you call it heat energy. So this becomes the energy, right? So I have this example under alpha decay. Let's take one example under beta decay. Example 2. Let's take an example under beta decay and explain together. Example 1, focus on alpha decay. Example 2, let's focus on beta decay. And then number 3, look at the two together combined. Example 2, under beta decay, randon undergo beta decay to emit 2 beta particles to produce an isotope of radium. Let's solve this problem, please. It says random, so random is Rn, so random is Rn. So Rn, in accordance to this first example, they didn't give us the atomic mass and the atomic number. They expect we know it. How? We just got the value here. So this is 86. Here is 86 as atomic number. Mass number is 222. So this man undergo a beta decay to emit. We are told that it emits what? 2 beta particles. That becomes 2 of beta particle is electron, minus 1 and 0, to produce an isotope of radon. So radion, radion, that's Ra. All right, let's get the atomic number and the mass number of radion. I said it's easy as, let's get atomic number. That's 86. This one here minus in a bracket 2 times minus 1. 2 times minus 1. That's all. I have 86 here minus 2 times minus 1 is what? Minus 2. 86 plus 2 plus 2. That gives what? 88. So I have 88 here as my atomic number. So radion is 88 atomic number. Here too is 88. No problem. Let's get a mass number. It's easy as I have 222 minus in a bracket 2 times 0. 2 times 0 is 0. So 222 minus 0. This gives 222. So the atomic mass is 222. That's why they said that to produce an isotope of radium. Now observe this and this one here. They both have the same atomic number, but what? Different mass number. So when two elements have the same atomic number but different mass number, is said to be an isotope. So an isotope is simply a process whereby two elements are having the same atomic number but different atomic mass. or mass number. All right, this becomes an example under a beta decay. Let's take an example that combines the two together. Something it says uranium 238 decays by emitting 2 alpha particle and 2 beta particle to thorium. Write a balanced equation. So let's try to get this. It says uranium. So by the way, uranium is U. This uranium, and I'm told that it has a mass of 238. I have 238 here. So by the way, uranium has an atomic number 92. So you should know that, please. Uranium 92. All right. This man here undergo. They said by emitting 2 alpha particle, that becomes 2 alpha particle are H, helium nuclide. So H2, I have 4 here, plus also 2 beta particle, that becomes 2 beta particle are electron, minus 1 and 0. So I'm asked, so next up, to thorium plus, thorium is TH. So thorium is the new element form. Let's try to get the atomic number of thorium and the mass number of thorium. So here's the concept, please. We said to get the atomic number of thorium is easy as I have 92 here, minus in a bracket 2 times 2 gives 4. That becomes 2 times 2. I have this way. This man is plus, but here's the concept. I'm focusing on what? What's it called? Decay. So I shall have a negative minus in a bracket. This 2 times 1, 2 times minus 1, that becomes 2 times minus 1. If I'm to solve this, I'll have the value here. So I have 92 minus, this is 4, minus 2 times minus 1 is what? Minus 2. Minus 1 is plus. So I have 92 minus 4 plus 2. This will give about 90. So thorium has atomic number 90. So I have 90 here. Let's get the mass number. That becomes 238. So I have 238 minus 2 times 4. Observe, 2 times 4. That becomes 2 times 4 plus, sorry, not plus, minus 2 times 0 is 0. So I have 0. This gives 238 minus 8 minus 0. This gives 230. So the atomic mass of thorium is 230. So this is how I get the atomic number and the mass number of thorium in this given equation. All right, this is how this works. So I've tried to explain the concept of natural radioactivity using the idea of alpha and beta decay. Let's explain the artificial radioactivity. Let's explain artificial radioactivity using some examples. So by definition, artificial radioactivity occurs when an element which is usually non-radioactive is made radioactive by bombarding it with a radioactive substance. Define artificial radioactivity. So artificial radioactivity are not radioactive, but I have to bombard them or collaborate them with a radioactive element, which are either your helium or your electron. Observe that I have aluminium. Aluminium is not a radioactive element, but I bombarded it with what? An helium, which is what? An alpha particle, to make it what? To make it what? To make it a radioactive. So the process of you bombarding a non-radioactive element with a radioactive element is said to be what? There, an artificial radioactivity, right? So observe that I have helium, He, this way, bombarded with aluminium, atom number 27. I have phosphorus, bombarded with, this is your neutron, right? And I have silicon combined with what? What's it called? Electron, right? To give you energy, right? Some of energy. I have this one here. All right. If you observe closely, let's see this is balanced. 2 plus 13 gives 15. Let's focus on the atomic number first. 2 plus 13 gives 15. Also, 15 plus 0 gives 15. 14 plus 1 gives 15. So to make the atomic number balance, so it's the balance equation. Let's check for the atomic mass. 4 plus 27 gives 31. 30 plus 1 gives 31. 30 plus 0 does not give 31, but gives what there? 30. So that's the concept there. And energy is being lost at this process. That's why I have plus energy. So an energy is one energy is being lost in this process. So this gives 30, sorry, 30, 31, 31. This gives just 30. So it means an energy is being lost. So I have this explanation here. So other example of artificial reactivity is simply combining lithium with neutron and also bromine with helium. So I'm just trying to understand the concept here. For artificial reactivity, the radioactivity are not the elements are not radioactive, but they can be made radioactive by bombarding them with a radioactive element such as your He, your N, and your helium, He, and electrons. So I have this concept of artificial radioactivity. All right, let's look at the next concept called radioisotopes. By definition, what's a radioisotope? The isotope are simply isotopes of elements that are formed by bombarding certain elements with a neutron, proton, or a deuterium. So whenever an element is being bombarded with a neutron, electron, or deuterium, is said to be a radioisotope. Example include, I have this one here. So I have this one example here. Observe that this crowbar is being bombarded with what? Neutron. So in this case, it's because what the a radioisotopes. Why? Because it's bombarded with what? A neutron. Now let's see what will be formed. So let's say I have this way. So first, let's see the element that will be formed here. So let's say I have, let's say for instance, I have to combine because I'm bombarding. So 27 plus 0 gives 27, right? So an element that has 27 as its atomic number is cobalt. So I say I have C, right? C. All right. The mass number becomes 29 plus 1. That gives what? 60. So I have of course, plus energy at the end, please. Always add any energy at the end. Energy. So I have this, please. Next task, I can see Br here combining with neutron. So the reason here is the concept, please. Whenever I see neutron or electron or deuterium combining with another element that is not radioactive, it means what? It's undergoing what? A radioisotope. So here's the concept here. 35 plus 0 gives 35. Of course, an element that has atomic number 35 is Br. So Br, I have Br here. 27 plus 1 gives 79 plus 1 gives 80. So I have 80. Of course, plus energy. All right, this is the basic concept behind radioisotopes. So I have this concept. All right, should we proceed? All right, from here, I have radioisotopes done. Let's look at yet the concept of nuclear energy. What's a nuclear energy? A nuclear energy is the energy that is released or given out through a radioactive process. So if I have, so all this energy I'm putting in the back, all this energy I'm putting in the back, energy. So it refers to as a neutral energy. A neutral energy is a form of heat, and it is energy produced when radioactivity is being processed or occur. So an element and energy is being released. The energy is called the nuclear energy. Now when it comes to nuclear energy there, we're looking at two concepts there: the nuclear fusion and the nuclear fission. So let's explain nuclear fusion and nuclear fission. By definition, let's look at the first one called the nuclear fusion. Nuclear fusion, these are simply the nuclear process in which two or more light nuclei combine or fuse to form a heavy nucleus with the release of large amount of energy. Let's discuss nuclear fusion. Nuclear fission, this is simply the splitting of the nuclei of the heavy element into approximately equal parts with the release of huge amounts of energy and neutrons. I just explained nuclear fission and nuclear fission. For nuclear fusion, here's the concept. I'm having a smaller element, like a smaller broken down element, giving you a bigger element. That's like a nuclear fission. And for nuclear fission, I'm having a bigger one, like 2235 is the bigger one here, being split into smaller smaller elements per se. So in the concept, I'm having, let's try to get the total atomic number and mass number. 1 gives you 2, balanced. Yeah, 2 plus 0 is 2, so it's balanced. 2 3 gives you 5. 4 1 gives you 5. So this one here is balanced. Atomic number is balanced, mass number is balanced. For this one here, I have 0 plus 92 gives 92. This one plus 1 here gives you 236, right? Yeah. So 56 plus 36 gives you 92. Similarly, all right, yeah. For this one here, this 3 times 0 is 3. So 3 times 0 is 0. So that becomes 0 plus 36 plus 56 gives you 92. Similarly, 3 times 1 is 3. So I have 3 plus 92 plus 141. So if I have 141 plus 92 plus 3, this gives about I have 2 3 3 plus 3. This gives 236. So that gives 236. Now observe that when I added this with this, gives me 236. What I have here is 235 plus 1 gives you 236. So this is balanced also. Now here's the concept. How do you spot out nuclear fission and nuclear fission? For nuclear fusion, observe that in this part here, you'll be having a smaller, see 2 and 3 are smaller, but in the product side, you'll be having 4 higher elements. So I'm saying that when it comes to nuclear fusion, the concept is that the reactant side has smaller elements, so smaller values, while the product side has a bigger value. For nuclear fission, you tend to have more higher values at the reactant side, while the product side has smaller values, right? So the value here are smaller than the value here. So this value here are bigger. 325 is bigger than 141, 92, and 1. So this is how to identify nuclear fusion and nuclear fission. Let's see some past questions under this and explain what it means, and then we're off with the class. Let's take some past questions involved in study of radioactivity. Number 1 says, when PB 210 having atomic number to 82 decay to 206 PB having atomic number 80, it emits dash. All right, I have, observe this please. I have 210 PB 82 decays to emit 206 PB. I have 80 here. So I'm asked to find if this equation is it undergoing an alpha particle, or one beta particle, or one alpha and one beta particle, or two alpha and two beta particle? How do I know? Observe this, please. Observe this, please. Here's a task. Let's say I have plus. Let's say I have an element here, for instance, right? So it means that if I add 80 with something, it should give me 82. If I have 206 with something, it should give me what there? 210. So the value I have here is 2. Value I have here is 4. So if I have 80 plus 2 gives me 82. 206 plus 4 gives me 210. So I'm saying that which element now has atomic number 2 and mass number 4? Of course, this is helium. This is He, helium. So it being helium means this equation undergo an alpha decay. That's option A. An alpha decay. An alpha decay. All right, example 1 done. Let's move to example 2. Let's do example 2. The radioisotope 235, uranium-235, decay by emitting 2 alpha particle, 3 beta particle, and a gamma ray. What is the mass and atomic number of the resulting dot element? Example 2 says the radioisotope 235, uranium-235. So I have uranium-235. I have an atomic number 29. I'm told that this man emits 2, so it undergo and emit 2 alpha particle. That's He. This is 2 and 4. Next up, 29 is 92. Sorry. So I just said I misplaced. I don't know. I said the correct. I wrote the correct thing down. I said the wrong thing. Please, 92 is the atomic number for uranium. So I have He, which is served as the emitting 2 alpha particle and also 3 beta particles. So 3 beta particles are electron minus 1 and 0. This one signifies beta, alpha particle, beta particle. Next up, and a gamma ray. So plus gamma is this. I'm asked to find atomic number. I'm asked to find atomic number. So that plus, let's say the element we're looking for, let's say it's X, for instance. X. Let's get the atomic number of X and mass number of X and see what element signifies those values. So here's the concept, please. Let's get the atomic number first. That becomes 92. 92 minus in a bracket 2 times 2. 2 times 2. All right. Minus in a bracket 3 times minus 1. That becomes 3 times minus 1. Of course, there's nothing here. Does that all? So that becomes 92 minus 4 minus in a bracket minus 3. 3 times minus 1 minus 3. This one is this. So next number have 92 minus 4. Minus is plus. So plus 3. It becomes 92 minus 4 plus 3 gives minus 1. This gives 91. Perhaps 91, please. 91, please. 91. 91. So I have 91 here. Let's get atomic mass. So this is 235. So that becomes 235 minus in the bracket 2 times 4. 2 times 4 minus 3 times 0. 3 times 0 is 0. This gives 235 minus 8 minus 0. This gives this gives 227. 227. This gives 27. Have the value here 227 here. So which element has atomic number 91 and mass number 227? Of course, the element is known as protactinium. Protactinium is simply the element which has its atomic number as 91. So protactinium, so X becomes protactinium. Why? Because it's that atomic number 91 and the mass number 227. All right, this is how you solve example 2. Let's do one last example and we'll call it a day. Let's do number 3. It says, what type of reaction is expressed by the equation? So I have the equation, says, so this is X, I have 1 plus, this is 2, I have X here, I have 1 here, undergo, this is 3, I have Y, I have 2 here, plus I have 1, I have N at 0 here, plus energy, so plus energy, plus energy, plus energy. Please, it says which type of reaction is represented? All right, is it nuclear fission or nuclear fusion? We said for nuclear fission, you have the higher values on the reactant, while the lesser value on the product. For nuclear fusion, you have the smaller values on the reactant, while they have the bigger values on the product. So here's the concept. The bigger value is here. So if I have a bigger value on the product side, this expresses the concept of of nuclear fission. So this equation becomes a nuclear fusion, right? So this becomes a nuclear fusion. Why? Because I have higher values on the product side than the reactant side. So I have this, please. Let's get the other one done. Let's do number 4. All right, number 4 says the product of the decay of phosphorus 32 as a beta emit is, it says phosphorus, that's P having 32 is the mass atomic number. So they expect that you should know the mass number, and the mass number is of course 15. This man emits beta decay, that's 0 minus 1. So they are asking us that what will be the element that will be formed. As you can see your options in the screen, right? So let's see what we'll get. Plus, let's say the element, let's say it's X for instance. Because 15 minus 1, that gives you 14. 32 minus 0 gives you 32. So check your option, 14 and 32. Which option fits in for 14 and 32? If I check my options here, sorry, please. We said this is not just one. We said it will be 15 minus, in a bracket, minus 1. That gives you 15 minus 1 is plus 1. That gives 16. Please, this man here is not just 14 but 16. So 16 and 32. That's option C. So that's option C. Option C is of course 32, 16. I have X. So this is sulfur. So the answer there becomes sulfur. Option C. It becomes the answer. All right. This becomes the whole concept behind radioactivity. I'll give you an assignment to try. So I'll show you the assignment on the screen. So you see the assignment displayed on the screen. Copy down the assignment and give me the answer to that. Is that question a nuclear fusion or a nuclear fusion? Give me the answer to that question in the comment section. Do also like this video, share to your friends and classmates, and also subscribe to my YouTube channel. All right, see you guys in our next class, and welcome to Excellent Link Academy.